Now we're going to go into matrix diagonalization. It seems like a total sidestep, but we're going to need it a lot for the next video. So if you're not that comfortable with the matrix diagonalization, please look at the other material that I have posted. The idea of matrix diagonalization is that you can transform a square matrix A into a product of three matrices, P at the -1, D, P, where D being a diagonal matrix. That is, it has some non-zero values on the diagonal and 0 everywhere else. If you don't know about this topic, please read about it. There is an external video to review this topic. Now that we have seen, or I assume we have reviewed matrix diagonalization, we can look more in depth on matrix exponential. So we have said just a minute ago in the video about ODE systems, that we can solve linear ODE systems by just taking the exponential of the matrix A times x. This is formally perfectly fine, but how can we actually compute the solution at this point? Well, let's look at the easiest option. So A is a diagonal matrix. It has some values on the diagonal and 0 everywhere else. Now you might have noticed that my writing here doesn't have A11, A22 on the diagonal, but has lambda1 and lambda2. This is because because the usual way to write eigenvalues is through the notation lambda, and we're going to see that eigenvalues are really important when we're looking at matrix exponentials. And furthermore, for diagonal matrices, eigenvalues and values on the diagonal correspond. So it's possible to write a diagonal matrix as the matrix with eigenvalues on its derivative, because they're the same thing. So let's look at A times A when A is a diagonal. So you're multiplying a string of zeros, and the only term that is non-zero is the value on the diagonal itself. That gets multiplied by itself on the second matrix. So A squared is the square of the diagonal. We don't have any extra term popping up. And if you keep doing this many times, what you have is that A at the power n is a diagonal matrix in which each element on the diagonal is taken at the nth power. This is great because it means that when we're looking at the exponential, that is a sum of powers of A, it's very easy to compute all these powers. It's just putting the elements on the diagonal at the power that we want. So we just take x and we put it inside the matrix itself, and then we look at what happens to each term of the diagonal matrix. So everything that is outside of the diagonal is still 0 because there is no non-zero term appearing anywhere. And each term on the diagonal is 1, given by the identity matrix at the very beginning. Then the eigenvalue that you're looking at times x plus the square of the eigenvalue times x squared divided by 2 factorial, and so forth. So we are left with something that is exactly the exponential of the eigenvalues we were looking at. So we can easily replace this with exponential of lambda 1x, exponential of lambda 2x on the diagonal of our matrix. So to recapitulate, if A is a diagonal and has its eigenvalues on the diagonal and nothing else, then the exponential of A is a matrix with the exponential of each eigenvalue on the diagonal. Remember, while this looks like a very nice formula, it does not hold that E at the power of A is equal to a matrix with the exponential of each single element. This is false. Let's look at another option. A is diagonalizable. What does that mean? It means that A is not diagonal per se, but there exists a matrix D that is diagonal, and P, a matrix P that is invertible, such that A is the product of the inverse of P times D times P. Now, the elements of D on the diagonal are indeed again the eigenvalues of A. And we have a very important theorem for dealing with these cases that says that if all the eigenvalues of A are distinct, so they're different, then A is diagonalizable. That means that the matrix D and P exists. So we can again look at the exponential of a matrix A as the infinite sum of powers of A. And now we replace A by P at the minus 1 dP. We replace it in the first term, in the second, and in the third. And what we notice is that, well, P and P minus 1 are next to each other. So these are the P and P minus 1 can just multiply by each other, make the identity, and the identity doesn't matter for multiplications. So we retrieve something that has a lot of D's and not a lot of P's. In this case, X is a scalar value. So we can shift it in the multiplications and put it wherever we want. So in this case, first we see that the identity matrix is P minus 1 times P, and then we have the situation in which all the terms in our infinite sum are always enclosed by P minus 1 at the beginning and P at the end. So we can take these terms out. And what do we have in the center? Well, this is the definition of the exponential of D. So we can rewrite the exponential of AX as P minus 1, the exponential of dx with D, a diagonal matrix, times P. And the exponential of the diagonal matrix is something that we know how to do. As a conclusion, if A is diagonalizable, that means that all the eigenvalues of A are distinct. Then we can write the exponential of A as a matrix product of two matrices that we know, and the exponential of the diagonal matrix in the middle. If there are repeated roots, it is still possible to compute exponentials, but it requires a little bit more work, and we will not look into that.